Okay, so in this video we're going to be looking at the 1D wave equation again, but this time the string is going to have a damping term, and as you can see here, the damping term results in the oscillations of the string eventually damping out and the vertical displacement going to 0 sometime t later. Okay, so you'll recognize this part from the 1D wave equation without damping. See, we're going to keep everything the same. We're going to keep all of the boundary conditions and all of the initial conditions and the initial shape of the string, the way that it's blocked. We're going to keep all that stuff the same. The only thing that's going to change is going to be the actual form of the wave equation. Okay, so this is all the work from the last video. I'm not going to go through everything again in as much detail, but this is the result that we eventually came to. Our new result is going to be similar, and you can actually derive this result from the new result that we're going to get to in this video, but there is going to be some differences, obviously, and it's going to lead to this damping effect. Okay, so the equation this time is different. So if you remember in one of my first differential equations videos, I talked about a damping force of a mass that's proportional to the mass's velocity. Well, here there's a similar take on this. The one-dimensional wave equation with the damping term looks like this. Okay, so you can see that the difference is this damping term here, where we say that the damping is proportional to the velocity of the string, which is dy dt. So again, we're going to take a to be 10, just random number, and I just picked the damping constant, the damping coefficient to be equal to 0.7. It's just kind of random, but it works, so let's work with it. Okay, so you can solve this problem using variation of parameters again. I'm not going to get too bogged down on the details, but roughly, when you use this as your trial solution and you plug it into the differential equation, you end up with this. So similar to the last video, there's a separation constant, and for convenience, usually they write the separation constant like this. Okay, so now out of this you can see that you can formulate two ODEs. So the two ODEs are like this. Okay, so when you have an ordinary differential equation like this, from the characteristic equation you can see that the solution to this equation looks like this. Because the roots of the characteristic equation are complex. For this equation over here, the characteristic equation looks like this. Okay, so when you find the roots of this equation, you can see that there's a real and imaginary part to it, and the solution for this equation ends up looking like this. Okay, where this omega, the angular frequency, is like this. Okay, and you can already see that the real part of the roots of this characteristic equation lead to this term here, this decreasing exponential term here, which decays and leads to the damping behavior. Okay, so plugging in the boundary conditions. Similar to the last video, I'm rushing through this because this is like my 5th video on separation of variables, and it'll be my last one. I think my next video is going to be on using the Laplace transform for partial differential equations. Okay, when you plug these values into here, and you remember the trial solution was y equals x times t, where x is a function of x and t is a function of t. So when you plug everything together and you multiply x by t and you plug in a is 0, which gets rid of this term, lambdas, and d is this term here, and then you combine those two, you end up with a solution that looks like this. And you end up with this. I just want to point out that I changed that 0.3 to 0.7 here, because that's my damping coefficient. Okay, so if you compare this to the solution to our first example, PDE4, the wave equation without damping, basically that damping term was 0, so our damping coefficient was 0. So here you can see that here's our damping coefficient. If this is 0, then this term is gone. There's our damping coefficient there again. If that's 0, then this whole term here is gone. So you end up having, oh, and that's 0, so e to the 0 is 1. So when our damping coefficient is 0, we end up with just this set of terms right here, which is the solution to our original equation, which is what we expect. Okay, so now to solve for these constants, again, when you look at your initial condition here, you see that you just end up with the same Fourier series that we had in the first example. So what does that mean? Well, it means that all of our coefficients are the same as in our first example, where n is odd. Okay, so this leads us to the following result. So this is our result, and I will show you the MATLAB code. Okay, so here's the code, and you'll notice that it's the exact same code that I used for the first problem, PD4. The only difference is I commented out the solution that we arrived at in PD4, and instead I inputted the solution that we just found. Okay, so you can see all the terms here. You can see the damping constant 0.7 there and there and there, all the spots it's supposed to show up. Here's our the coefficients that we found, and you can see that when I run it, the vibrations in the string damp out over time. Okay, so let me just change the step size there to make it go a little faster. And you can see that this is a much more realistic representation of a vibrating string. Vibrating strings just wouldn't vibrate forever. So this is an example of a situation where the PDE models the real world situation much more realistically. Okay, so thank you very much for watching.